All right, people. I know I really don't have a voice, but I'm going to try and use whatever I've got. This is ICCRG. If you're here for anything else, you might be pleasantly surprised. Because we have more fun than anybody else does. Can somebody get the doors in the back, please? Okay. I'll need, well, I'm going to start now because we are at 1:32. Can everybody understand the words I'm speaking? Good. Thank you. Well, I almost thank you, Martin. That was very, yes. Thank you. All right. So note well, slides. Note well, important. If you've not seen this before, please look it up. Google IETF and note well, and you'll find good information about IPR disclosures, about the work that gets discussed here. If you're not familiar with this, please familiarize yourself with this before talking about anything. Sorry? Please Bing this. Or what is it, DuckDuckGo this? The agenda is as follows, but before we get into the rest of the agenda, I need a Jabber scribe. Somebody on Jabber. Jabber scribe, Jabber scribe. Thank you, Miria. Miria's the Jabber scribe. Who's taking minutes then? I'm going to name you in a second. We need somebody to take minutes. Thank you, Stuart. Thank you again. Okay, so we will be talking about BBR V2, which is a brand new BBR, if you've not been paying attention. So Neil's here, he'll be talking about that. And we have an exciting, what do we call it? LEDBAT double presentation. What's that? Double feature, thank you. That was my brain's also not really functional at this point. We have double feature on LEDBAT. We've got Praveen from Microsoft talking about LEDBAT++. Some of you may have seen that before, but it was popular, so we're bringing it back. And we have our LEDBAT from Marcelo, which will build on this to do receiver side congestion control. So this is going to be interesting, I hope. And if time permits, we might have some time for a presentation from Anna or Ronnie's group at Huawei. Before we get into these wonderful presentations, I just want to take a few minutes of your time to discuss a direction in which we are trying to go. So this is just kicking off a discussion. This is getting the conversation started. ICCRG has published documents in the past, and we would like to start doing that again. The context is that there's new and important work coming through ICCRG now, and this is something that we are seeing as consistent presentations coming through. These are experimental algorithms. They need continuous review. They need feedback from the community. They go through iterations and they come back. This seems more and more like a process that should turn into something sort of an adoption, some sort of publication eventually. BBR and LEDBAT++ are strong candidates at this point. The brand new HighStart++ and also Paste Chirping are early candidates, but we'd like to see this sort of practice start to happen. I'm completely aware of the fact that this needs a few things and has implications. This needs commitment from the authors to keep coming, doing things that they might otherwise not do. This needs us to agree on what it means to adopt something, what it means for a research group to adopt a document, so to speak. It also does mean that we need to agree on what it means to publish a document. What do we, if the ICCRG says that it's going to get published as an ICCRG document, what should that signal to the community? We do need to figure this out, but I think we can solve these problems. This is not intractable. So that's something I'd just like to kick off a discussion. If anybody has any thoughts on this, I'll leave a couple of minutes. Otherwise, we can continue this on list. Michael Welzel, no thoughts? Seriously? Brian.
Hi, I was closer to the microphone, so I stood up. Brian Trammell. Do it. Is Spencer here so I can borrow back my Panergy chair hat? So Panergy basically has this a more focused set of research questions that it's looking at least right now. It might, mutate into something a little bit broader. And we've sort of kept those in internet drafts, which are adopted internet drafts for the thing, for the research group. And the process runs a whole lot like a working group, right? So you could basically just port the process over, runs fine. One question that we have in terms of the types of documents that we have in the research group are these things that we basically just want to keep the document as an internet draft and keep it alive within the research group, where that draft IRTF Panergy label at the front means this is something that the research group is thinking about, not necessarily that it's ever going to be published as a document, right? So something that's talking about sort of frameworks for how you would consider research in congestion control algorithms. We're not really sure that we're going to publish any of the documents out of Panergy as RFCs. I think that clearly the experimental RFCs for some of the experimental algorithms, that makes sense to publish here. But you might also want to consider that some of these documents, you might want to just sort of keep them as research group IDs, as sort of kind of like living documents for what's going on. Thanks.
Michael Welzel, yes, I very much agree with it. In my experience, the issue the issue with doing this, my experience with telling people that we can publish things directly in ICCRG was that their response usually was that they have this business in the other room and it's a very interesting idea, bye-bye. Something, I don't know, I don't know, probably it just smells too much of this is a useless IETF document, or I don't know. I just never had people wanting to do it.
Gary Fair has been attacked by the mic. As TSVWG chair, I think I want to try and understand what the difference is between publishing something here and taking one of these to TSVWG, which you could do as well. So there is a difference because these groups are different and the process is different, and that doesn't mean that you shouldn't do it here and be able to do it there, but we need to be clear to the community that reads these what that difference is, and I don't know yet.
So this is deliberately not going into that. But
yeah,
absolutely and 100% aware of the fact that I think that the leadership and the community are all confused about where these documents ought to go at the moment.
Okay, Magnus Westlund. I get to almost take on my former transport area director. This actually goes back to when I was AD previous term, because that's when me and Lars Eggert worked quite hard with the then set of ICCRG shares to establish this process of trying to bring in things into ICCRG, do experimental specification first, and then when algorithms were proved, we could move them on into the IETF. That was the intention of the process back then, 10 years ago. And I think there's definitely value publishing specs experimental as a starting point, and then see what, when we get high maturity and deployment experience and all those things, we can move them into IETF when they're suitable. So.
David Black, the other TSVWG chair who happens to be here in Montreal, I mostly want to plus one Magnus's view of how the world should work. There's a very nice analogy between ICCRG's relation to the transport area with CFRG's relationship to the security area. This is where the deep expertise exists on the congestion control algorithms, including every last little detail that you have to get right or else. And like Magnus, I'd be very comfortable looking to this group to nail the algorithms to the floor, and then the rest of the IETF, TSVWG, and beyond can figure out how to apply them in protocols.
So just to be clear, David, for a moment, and maybe Magnus as well, are you suggesting that we can keep that we publish experimental documents here?
If you find that useful as part of maturing and nailing the algorithms to the floor, go for it.
I jumped up when Michael said, there wasn't much interest in people wanting to write things in the ICCRG, and I wondered whether, going back to Magnus's, sorry, I'm Bob Briscoe, going back to Magnus's point, that where this process came from was where an IETF group would ask the ICCRG to do expert review. And that's sort of broken apart because there's so many transport protocols now that would use the same congestion control. And so it occurred to me that TSVWG might be the place that would ask ICCRG now for all the transport protocols. And it would be and then that might give a bit more cachet to having a ICCRG RFC about your congestion control, because it's something that is used for a number of transport protocols. Yeah, there is that.
So Mia Kulevin, as an individual, my opinion is that we should not talk about processes right now, and it doesn't really matter. I would be super excited to work on congestion controls in a collaborative manner where we all talk about problems and finding solutions together, write them down, make sure that we have a description which is readable and implementable and we all like, and then we can figure out what to do with it.
So my name is Michael Scharf, speaking as TCPM chair. Sorry I came late because this slide was not on the agenda, so I haven't seen it. It was another room. I just want to point out I disagree with this, what is written here, and it would require rechartering TCPM, which I also disagree right now. So I just point a big -1 on this one here. I don't know what has been said before, but I disagree with what is written on the slide. I disagree with the publication of experimental algorithms such as HighStart is ICCRG because this is in charter of TCPM. So if the authors want to come to TCPM, the charter allows that, and I disagree with changing that part of the charter right now without having a bigger process discussion.
Yeah, but it doesn't matter. I mean, this is ICCRG, right? If ICCRG wants to do it, they can do it.
Sure, but if that implies that people will come to TCPM and say that we don't do things that are in charter, then this is a different story.
So just to be clear, the slide here does not talk about TCPM. The slide here talks about what ICCRG is going to do. If this means that people start showing up to ICCRG more, that's a good thing for ICCRG. I think your point is right that there's scoping overlap between the two for sure. And maybe this is something that we need to go off and discuss what to do about. But I would like to have the conversation about publication through ICCRG here.
That's a fair point. But just as I said, the last point here is a TCPM individual draft suggested to TCPM right now. So there is overlap in what you have here on the slide.
But just to be clear, also that's not been adopted by TCPM yet.
So, Matt Mathis, I think at the end of the day, what we're arguing about is what you need to do in order to put -ICCRG- in a doc name. And maybe that should just be a self-selection process to help some of us find other documents easier. And just recognizing that sort of the rules are anybody can put -ICCRG in a file name is sufficient to address the topics on the slide.
Colin, you'll have the last word.
Hi, Colin Perkins. I mean, I clearly think, publishing congestion control algorithms is clearly in scope of ICCRG. Experimental algorithms, potentially even informational algorithms, if we believe something is mature enough, I think it is something ICCRG could certainly do. Equally, this is the IETF and doesn't set standards, so we need to be clear on boundaries and the scope of what we're doing, and we need to very much understand the relation with the IETF groups. And someone brought up the Crypto Forum group earlier, and that's been someone brought up the Crypto Forum research group earlier. I think one of the difficulties with that group has always been knowing precisely where its boundaries lie and what's research and what's the standards. And I think they generally get it right, but it's always something that they have to be very careful of. So I think if you're going this way, I think it's a good thing, but be careful of the scope.
Thank you so much for that discussion. We'll have to continue this later, either on List or in Singapore. But we're going to move on next to Neil's presentation on BBR. Oh.
Testing. There we go. We all set? Okay. Hi, I'm Neil Cardwell. I'm going to talk about BBR version 2, a model-based congestion control, give a quick update of some work that is going on in our group at Google. This is joint work with Yu Chung and Sohail, Priyaranjan, Yusuk, Ian, and Victor, and Bin, and Matt, and Van Jacobson. Just a quick outline. Wanted to talk about an open source alpha or preview release that we sent out last night. We'll talk about the status of the code, some quick lab test results to give a flavor of the behavior and where we're trying to head, and then talk about the deployment status at Google and wrap it up. So we've just yesterday released an open source alpha or preview release of the TCP BBR v2 code. And the quick release is coming very soon as well, I think probably later on today. And the goal here of this particular release is to enable research collaborators to do some testing, try out their ideas, get more real-world test miles on BBR. And we encourage researchers to dive in and evaluate the algorithm, the code, help improve the BBR in general. And of course, we welcome patches with solutions to issues that we're aware of and issues that researchers find along the way. The slides have the URL with a hyperlink that you can drill through to get to the TCP and quick versions of the code. And in particular, I would also note that the TCP source tree there also includes the scripts that we use to run these tests and generate the graphs for this particular slide deck, so that people can see what the details are and can use those as perhaps a starting point for experimentation. And I would just remark that these tests are using network emulation using the Linux NetM QDisk. And for an overview of the algorithm itself, I would point people to the slides in the video for the IETF 104 presentation, as well as some discussion in the IETF 102 slides as well. So what's new and what's changed between BBR version 1 and BBR version 2. We've talked about this a little bit before, but just to sort of recap, the properties that we are maintaining between version 1 and version 2 are obtaining high throughput with a targeted level of random packet loss, and also being able to bound the amount of queuing delay that a flow is causing, despite the fact that it might be traveling through a very buffer bloated path. But then the improvements that we're looking at from version 1 to version 2, as we've discussed at the previous IETF, include first, improved coexistence when BBR v2 shares a bottleneck with Reno or Cubic, much lower loss rates for cases where the bottleneck buffer is on the smaller side, higher throughput for paths with high degrees of aggregation, which is common with Wi-Fi bottlenecks, DOCSIS, cellular, they all use a lot of aggregation. V2 includes support for DC TCP or L4S style ECN signals. And we've also reduced the amount of throughput hit that the flows take for entering the probe RTT phase, where the flows try to cooperate to expose the min RTT of the path. And so in the following slides, we'll run through a few tests just to sort of illustrate the general flavor of the behavior and illustrate some of the core properties that we've maintained or in some cases added to V2. And throughout these, the metrics that we're looking at include throughput, queuing latency, retransmit rate, fairness, that sort of thing. Just a tour through some lab test results. So first, if we think about surviving random loss, V2 continues to maintain the property that V1 had, that it's able to achieve high throughput even with a targeted level of random packet loss. So here is an example of an experiment where we take either one flow and it's either Cubic or BBR version 2, and we send it through an emulated path where the link bandwidth is 1 gigabit, the min RTT is 100 milliseconds, as the BDP of buffer, and then we do a bulk transfer with a particular level of random packet loss, spanning orders of magnitude. So the x-axis is log scale here. So we can see that Cubic is achieving low throughputs, as is well known. It's very sensitive to packet loss, whereas BBR version 1 is achieving a high throughput up to about 15% loss rate. We'll sort of see the corollaries of this in some of the follow-on tests. But with BBR version 1, that level of loss tolerance is sort of implicit in the magnitude of the bandwidth probing that it's doing. By contrast, BBR version 2 is an algorithm designed around including an explicit loss threshold of a level of packet loss that it's trying to target. So for example, here, the sender was configured with a loss threshold of 2%, which means that if the short-term or sort of instantaneous loss rate that it's measured over the last round trip time is 2%, it takes that as an explicit hint that that's an operating point that is has too many packets in flight. And so it will end its bandwidth probing and then try to leave some headroom in the path for other flows to obtain. So that's why the curve has this shape here, so that you can see at low random loss rates, it's achieving high throughput, but it's not quite as high as BBR version 1 because it is trying to explicitly leave some headroom in the path for other flows to discover available bandwidth and to keep queuing and losses low. And then you can see that the BBR version 2 throughput sort of is reduced right around the 1% to 2% range there, which is because of that explicit loss threshold of 2%. Why does it fall off at that point? Well, if you sort of configure 1% random loss, then obviously the losses are going to vary round trip to round trip time, so you get this sort of falling off in this flavor. So that's one example. Another here, if we take a scenario where we've got a bottleneck with deep buffers, one property that we've carried over from V1 to V2 is that BBR is able to use its model of the network path and generate an estimate of the BDP of the path, and then bound the in-flight data based on that estimate to keep queuing latency reasonably low. So here's a test that's very similar to tests that we showed way back in IETF 97. So this is showing either 2 cubic or 2 BBR or BBR2 flows entering at staggered times. The link bandwidth is 50 megabits, min RTT is 30 milliseconds, and then we run a bulk test for a while at various buffer depths. And here on the x-axis, it's the buffer size as a multiple of the BDP, and then on the y-axis is the median smooth round trip time sample that we obtained. And you can see, as is well known, cubic will sort of fill any buffer you give it quite quickly and sort of hang out at that buffer occupancy. So as the buffers are bigger, then your RTTs are always bigger. Whereas BBR version 1 and 2, no matter the buffer depth, they will have their estimate of the BDP, and they'll bound their in-flight based on that to keep the latency within a more reasonable range. So something new in BBR version 2 is support for DC-TCP or L4S style ECN signals. So I have a couple slides here with an experiment with that kind of ECN. So the emulated scenario here is a 1 gigabit path with a 1 millisecond round trip time. So more of a data center style scenario. The bottleneck here has essentially a FIFO with a maximum depth of 1,000 packets, which is 12 milliseconds at this bandwidth. But the interesting thing here is that it's doing DC-TCP or L4S style ECN marking on packets that had more than a 242 microsecond sojourn time, which is basically saying once the queue gets to be 20 packets or more, then there's a sort of step up and you get ECN marks on packets for queues of that length or longer. And so the behavior we can see here in this kind of scenario is that for BBR version 1, it doesn't use ECN. And so as you add more flows on the x-axis, you can see that the queues get quite long and in fact tend to hang out right around 12 milliseconds. And that's largely because this test is only 10 seconds, and so the flows are unable to sort of loosely synchronize and coordinate to expose the min RTT of the path. And so BBR is unable to bound the in-flight in a way that we'd like on an experiment this short. By contrast, if we look at DC-TCP and BBR version 2, they're able to use those ECN signals to keep the queue right around the ECN marking threshold for smaller numbers of flows. And only at very large numbers of flows do you start to see it make excursions above that target range, with BBR2 being slightly more aggressive in its probing and thus having slightly higher RTTs with larger numbers of flows. If we look, so that's the latency picture in this kind of experiment. If we look at the loss rate picture, it's even more dramatic. Notice we've switched to a log scale on the y-axis because the BBR version 1, because it doesn't have time to learn the min RTT of the path, it allows the queue to be quite long, and the retransmit rate is just about 10% at higher numbers of flows, whereas of course the BBR2 and DC-TCP flows are able to maintain very short queues most of the time and have retransmit rates below 0.1%. So in the next experiment, we're illustrating another component of the BBR. Oh, sorry.
Can I just ask for clarification?
Yeah,
on
of
the previous
course.
Slide?
Sure.
Does the fact that those plots only start at 10 mean that it was 0 before 10? Or?
Yeah, because of the log scale, I was unable to get the zeros to show up. But yeah, if with one flow, of course, DC-TCP and BBR2 have zero drops.
Or 2, 3, up to 9.
Oh, there were, I only tried, what did I do? I did 1, 4, 10, 40, and 100. So at 1 and 4 flows, they had 0 drops. So another property of BBR version 2 is it has an explicit strategy for coexisting with Reno and cubic flows within a particular performance envelope. And this slide is just to sort of illustrate the flavor of that. Obviously, if you're talking about fairness, to do a complete evaluation is a very large n-dimensional space, lots of tests you need to run, but this is just one to illustrate some of the key dynamics here. So this is a bulk throughput test where there's one cubic flow and one flow that's either BBR or BBR version 2. It's sort of a 50 megabit bottleneck with a 30 millisecond min RTT, and it's a 3-second bulk throughput test with varying buffer depths here on the x-axis. And then we're showing the throughput of the BBR version 1 or version 2 flow, and then basically cubic gets the rest. So we can see here at lower buffer depths, BBR version 1 grabbed, sort of 43 to 45 megabits, whereas BBR version 2, because it has an explicit strategy about how it's going to probe for bandwidth and bound its in-flight, it's able to have a throughput that's much closer to the approximate fair share there at reasonably low buffer depths. And of course, as the buffers are deeper and deeper, the cubic tends to build such enormous queues that BBR's throughput does tend to gradually fall off as the buffers are deeper and deeper. But we expect in the common case the buffers should tend to be around 1 BDP or 2 BDP in well-provisioned networks. So we expect that the common case should be quite reasonable. So another aspect that we wanted to highlight was that BBR version 2, because of it uses loss as a signal and uses that to dynamically adapt the amount of in-flight data it's willing to maintain. It has considerably lower loss rates than V1 in shallow buffer situations. So in this experiment, we're looking at the retransmit rate for an ensemble of bulk flows. Here the link bandwidth is a gigabit, min RTT is 100 milliseconds. It's quite a big BDP, and then it's a 5-minute test. And the buffer here is very tiny relative to the BDP. It's about 2% of the BDP. But that can be quite representative of the situation you have if you build a high-speed WAN out of commodity switches with shallow buffers. This is the kind of scenario that the flows will need to deal with. And so here we can see that cubic, by virtue of its design and sensitivity to loss, keeps the loss rate quite low. BBR version 1, because it is agnostic to loss and because of a couple other factors, tends to have tends toward a 15% loss rate if there are large numbers of flows. And you can see that in the BBR version 1 line. By contrast, BBR version 2, because of its model is more rich and includes loss as a signal. To feed that model, it's able to keep the loss rates bounded in the region that is below its targeted loss threshold. Was there a question that you wanted? Okay, thank you. So those are the lab tests that we wanted to sort of run through to convey a flavor. Obviously, this algorithm in the code is still a work in progress, and obviously more tests will need to be run, but we wanted to sort of convey the flavor of where we're at and where we would like to head and the properties that we'd like to maintain and to add. So a quick note on the status of the algorithm in the code. So there are some remaining issues that we are aware of in the BBRv2 algorithm where we'd like to improve things. It can happen that flows that experience ECN or loss early on in their lifetime, but never thereafter, sometimes don't reach their full fair share. we can have queue pressure that's higher than desired when there are large aggregates of BBR-V2 flows. And it's also the case that the ECN response is not really well tuned for very long RTTs in the hundreds of milliseconds. And it's also not quite tuned for cases with more flows than slots in the BDP. And I would note that both of those issues are sort of shared with DCTCP, which is also so far intended and deployed so far for cases within a data center. So these are sort of not problems unique to BBR version 2, but sort of more general in the ECN ecosystem. And I'm glad that there are people doing work in this area in the L4S community. And of course, we're continuing to refine the algorithm, and we welcome ideas about how to handle all of these issues. So where are we in our deployment of this code? As I mentioned in March, we do have a global experiment running on YouTube for a few % of users. And what we see so far is that it has much lower queuing delays than Cubic and even slightly lower than BBR version 1. It reduces considerably the packet loss rates versus V1 and gets them closer to Cubic than V1. We're also using this code internally in experiments between and within some Google data centers. And what we're seeing there is that BBR-V2 has lower tail latency compared to the previous DCTCP style congestion control that was that's deployed for TCP within Google data centers. And we also, in our deployment and testing, we found an really interesting performance issue with the Linux ACK implementation that turned out to be a surprisingly high impact issue for data center performance, which we can talk about offline, but the basic flavor is kind of interesting, where the Linux acknowledgement code actually does not just check to see if you've accumulated more than one MSS of unacknowledged data. It also wants to be able to advertise a receive window that's as big as the previous receive window it advertised, which essentially means that it very often ends up waiting for the application to read all of the data out of the socket before it then sends an acknowledgement advertising the same. And I can see Matt frowning over here. And before it decides to send an acknowledgement, which can sort of include the application in the RTT loop of the congestion control and cause some serious latency issues. Anyway, that was an interesting issue, and it's a common issue in the core TCP stack, but we happened to run into it during this testing of this transition. We can talk about it offline if you're curious. Anyway, we're continuing to iterate using both production experiments as part of the gradual rollout and also controlled lab tests. So in conclusion, we've open sourced a first sort of alpha or preview release of BBR version 2. It's ready for folks to take it out for a spin in a research experiment context. And we obviously invite researchers to share ideas for test cases or test suites, metrics that they think we should be looking at. Sharing their test results is great. We're more than open to algorithm or code ideas or patches, and we're always happy to look at packet traces if you're taking it for a spin and run into a surprising issue. And in conclusion, work on BBR-V2 continues, both at Google, and we're also in communication with the FreeBSD TCP team at Netflix, who is also working on BBR as well. So yeah, any questions or comments? Thank you.
So Gary Fairhurst, thanks for bringing this here, because it's significantly different to the previous BBR instances, and it seems to be heading in a really good way. How much data have you on different experimental results in your labs? Because it looks like your points didn't have a confidence intervals or anything, so I'm kind of wondering whether you looked at lots of different scenarios, different delays, different traffic mixes, or whether it was really just a first cut.
Yeah, I think I would characterize this as the first cut to give a sense of the flavor of the behaviors that we're looking for, the properties that we're looking for. And I agree and take your point that a congestion control needs a lot more experiments than the ones we showed on this slide before you say, you're ready for, yes, to illustrate.
As I said, I'm pleased you brought this here. I'm curious about the high RTT thing because I have slides later on in the IETF about high RTT and other things. Do you think there's a way we could look at high RTT in this and figure out what to do?
You mean for the ECN and high RTT question?
Yeah.
Yeah, absolutely. So I think the direction that so I actually have I'm working with an intern right now to actually do experiments in this direction. I think my hunch is that what makes sense would be to include a response to ECN that is in the rate space, so that flows with different RTTs, if they're responding in a rate dimension, then everybody can respond in a similar way, despite having different RTTs. The issue with long RTTs and a purely C1 based algorithm that sort of happens immediately is the long RTT flows in the stream of ECN signals they get will sort of see an oscillation between ECN marked and clear, and it can happen on the scale of milliseconds. But if your if your RTT is 100 milliseconds, you may see a whole saga of up and down and up and down. But that means that every RTT of yours has ECN marks, and so using a classical style algorithm, you do multiplicative decrease every single RTT of your life until you converge down to a C-wind of 2. And if you're sharing with a flow that has an RTT of 50 microseconds and it has a C-wind of 2, it's quite happy. It's got a nice high throughput. But obviously, if your RTT is 100 milliseconds, your C-wind of 2 makes you very unhappy. But I think if all the flows respond in rate, by reducing the rate, that might allow us to have good solution here.
I think that's fun. I'd love to see more of that.
Okay, thank you.
Thanks, Neil. Martin Duke. First question, are you planning to do a draft of V2? And if so, how long could we expect to wait?
Yes, so one of our next to-do items now that the code is out there is to update the internet draft that currently is describing V1 and update it to cover V2. That is definitely something we agree is important, and we know it's particularly important for folks that aren't part of the open source ecosystem. So yes, that's on our to-do list.
We actually have an independent implementation. We find it very useful to have fixed points like the drafts rather than just trying to track your code.
Sure, okay.
Second question, can we return to the loss versus throughput graph, which I think is the first graph in the presentation?
Yeah.
Yes, okay, so I'm not sure I completely understood what you said here. So the cliff at 2% is a purely the result of configuration parameter?
That's right. That's right.
Okay. So that's fine. So if you didn't care about loss rate, you could just turn it up to, I guess that's 20, and you would essentially match the BBR1 curve, at least where the cliff is.
I believe so, yes.
Okay, but going all the way to the left edge of the graph, you're sacrificing about 10% of your throughput. And is that, so what is the trade-off there is that you are friendlier to cubic in that regime?
The basic flavor there is that BBRv2 is trying to leave some headroom in the system, either in free slots in the buffer or free slots in the wire, so that newly entering flows can grab some bandwidth without causing massive packet loss, and so that flows with lower throughput can discover that more bandwidth is available, again, without causing massive packet loss. So this is kind of similar to, for example, the rapid convergence mechanism in cubic, where if cubic thinks that its fair share is falling because somebody else has entered, then the cubic curve actually sort of spends a lot of time at 85% of the previous W max instead of 100% in order to leave headroom for other flows to sort of discover that there is more bandwidth available.
So mostly fairness, but you're also gaining some RTT benefit.
Yeah, exactly. So
Okay.
it's primarily been motivated by fairness, but also it reduces queue pressure and latency and packet loss. Yeah.
I'd also like to point out that Praveen is waiting in the
Yep.
queue. Thank you.
Okay.
Praveen next and then Jake, and I'm cutting off the mic line there. Praveen, you're up.
Can you hear me? Hey, can you hear me?
Your voice is breaking up badly, Praveen.
Can you hear me now?
Yes.
Okay, so first question is, why the particular choices for buffer sizes? I noticed that you went from 1 time BDP to about 100 times BDP, and for shallow buffers, 0.2 times BDP. So the question is, why did you select those sizes?
I had a hard time making out the audio. Did anyone else catch your question?
Praveen, first you have to It's echoing back in here. Oh, we lost him. Praveen, if you can mute your mic when you're not speaking, that will be helpful. So if you come back on. In the meanwhile, Jake, go on.
Okay, yeah. Hi, Jake Holland. With regard to the L4S style ECN marking, that's referring to the receiver response being 1 CE bit per CE mark, or is that?
Yeah, so it's referring to both the fact that it's expecting the ECN marks to happen at a low threshold of Q, and the fact that we are expecting the receiver to reflect the ECN marks on a sort of per packet basis rather than echoing the CE marks as having been experienced for an entire round trip time until that's acknowledged with the CWR bit. So it's the essentially DC-TCP style ECN. Yeah.
Did you try the ECN with like the home routers that do the marking? There's some.
No, we haven't tried that yet. My understanding is that most of the home routers that do ECN marking are RFC 3168 style. And we don't really intend to have BBR v2 use that style of ECN. Yeah.
Okay, thank you.
Thank you, Neil.
Yeah, thank you.
Yeah, sorry, Praveen is trying to get a headset, so if you can do the RLEDBUT stuff first and then come back to Praveen later, so we make that part at least work.
It'd be better if we could do, thanks again, Neil. The plan was to have Praveen do LEDBAT because our LEDBAT sort of builds on that. What do you think, Marcelo? Does that work for you? Right. Well, that's.
He said he would also be willing to give it a shot without the headset, but I'm not convinced that it will work.
But then he won't hear anything from us if you want to stop him or something like that. There, if he wants to give it a try, we can give it a try. Praveen, you're probably hearing this. If you want to give it a try, come on, let's give it a shot because it might be better if Marcelo follows you. Can you hear us?
Yes.
Okay, that's interesting. Praveen, mute your mic first. So if you can speak, if you can mute your mic.
Yeah, I'm trying.
And then we will have to wait until they talk to ask questions, but I think that's perfectly all right. Yours is not a long talk, it should be about 10 minutes. Does that seem reasonable? Okay. Right, but are you able to hear us, Praveen? I can't hear you.
Can you hear me now?
No, your audio's breaking super badly.
Okay, so let me try to figure out the headset situation then, and you can go with Marshall first.
So can you move back from the mic just a little bit?
Can you hear me now?
Okay, let's do that. We'll move on to Arlet Bat, and we'll see when you have headset.
Okay. Thank you. Okay. Good afternoon. I am Marcelo Bañulo, and I'm going to talk about receive-based lead-bat mechanisms. This is work that we have done with Alberto, Ana, Praveen, Daniel, and Gabriel. So, I guess, well, more or less. So I guess everyone here knows what lead-bat is, right? Lead-bat is a congestion controller that provides less than best effort. Essentially defines a queuing delay target T, right, and increases and decreases the congestion window based on whether the measured queuing delay is above or below the target. Right, the queuing delay is based. The queuing delays infer from the one-way delay experienced by the packets. So lead-bat, there has been a few shortcomings identified regarding lead-bat. In particular, it exhibits poor inter-lead-bat fairness properties, right? And there have been reported difficulties measuring the one-way delay, in particular in TCP, even if you use the TCP timestamp option, right? The reasons for these are several, including the fact that you don't know what the timestamps are expressed on, and also that when you have clock drift, it's very hard to measure because you're using these measurements in order to try to determine how much you're sending. It's hard to distinguish error from load, right? So. Jana, I'm having this. Can you make it so that when I click, it actually moves? Yes. Thank you. Okay, sorry about that. So, what we are proposing here is a receive-driven version of lead-bat, right? So the idea that we are proposing here is we're going to make a congestion controller that runs on the receiver, right? That is less than best effort. It's inspired in lead-bat. Well, it's very close to lead-bat++. That's why it was interesting for Praveen to present lead-bat++ before, and I present this first, but later, but that's fine, right? So the idea here is the congestion controller will run in the receiver, right? And the receiver will control the sender through the receive window, okay? One significant change is that we're going to measure the RTT instead of measuring the one-way delay. So we're going to estimate the queuing delay using the RTT rather than the one-way delay. So what are the motivations? Why we want to do this? So we have essentially three motivations, two regarding deployment models. One is, this is widely used for distributing operating systems updates, right? Some operating systems updates are being done through CDNs. And there has been observed that in many cases, CDN surrogates do not support lead-bat. And also, it's hard to convey, well, there is no signaling to convey, if they did support LEDBAT, which content must be distributed using TCP cubic, and which one could be distributed using LEDBAT. Right, so the situation is that the operating system gets uploaded to the CDN using LEDBAT because the source actually supports LEDBAT, but the distribution from the CDN surrogate to the client is not benefiting from LEDBAT, right? If we have a receive-based version of LEDBAT, this could actually enable the transfer using LEDBAT from the surrogate that is oblivious to LEDBAT to the client who is actually will be controlling using less than best effort congestion controller, right? A similar situation occurs when you have something like a proxy or a firewall or stuff like that that terminates the TCP connection, right? So the leg between the source that is using LEDBAT to the proxy is protected by LEDBAT in the sense that it is using LEDBAT, but the leg between the proxy and the final client is no longer using LEDBAT, right? So if you have a receiver-driven version of this, this would enable the use of LEDBAT in the second leg, right? And the other one is regarding how mobile device, for instance, in this case, right, that is downloading content from multiple sources, could actually enable some way of distinguishing priorities, if you want, or what type of what type of traffic he's willing to devote most of his bandwidth, right? So let's suppose in this case that you have a mobile phone, you're having you're watching a video, and then you receive a WhatsApp call. One thing that you may want to do is use, in general, when you're watching the video, use TCP, and then or downloading your files or whatever using TCP, and then when your phone call comes in, you may want to start using less than best effort for your background downloads, right? So if you are able to, if you enable the client to determine which flows are LEDBAT and which flows are regular TCP, then you will empower the client to manage its incoming link capacity by assigning different congestion controllers to different flows, right? So these are the three main use cases that we have in mind: CDN, distribution, proxies, and enabling the user to define its preferences by setting different congestion controllers. Okay? So this is in general about the algorithm. This probably falls more into LEDBAT++, but the goals for the design is basically essentially what I assume the original LEDBAT designs goals were. That is, if you have some latency sensitive, delay sensitive traffic like VoIP, when you're using LEDBAT, you should not add, the delay that it adds should be bounded to some target, right? If you have several LEDBAT flows, they should be fair between each other, right? They should equally split the traffic. If you only have LEDBAT, you should be able to use the full capacity of the link. And if LEDBAT is competing with standard TCP, best effort type of congestion control, then basically LEDBAT should move away and give most of the capacity to the TCP flows. So the algorithm that we are proposing is essentially we are using the round trip time in order to estimate the queuing delay. So we measure the base round trip time as the historical minimum, and we measure the current round trip time as a filter of last few samples. We estimate from that the current queuing delay. We define a target for what should be the queuing delay. And we essentially build an additive increase, multiplicative decrease based on how much you are above the target, right? So if you're above the target, you do if you're below the target, you do an additive increase. If you're below the target, you do a multiplicative decrease. Okay? So this was most about LEDBAT++, that is the congestion control itself. Then I'm going to dive deeper into the details on how do you do it from the receive side. Right, so we're going to do this controlling the receive window. So the first observation is the receive window has already been used for something, right? You use it for flow control. The idea here is you will calculate a congestion window on the receiver. You'll obtain a value. You will obtain a value from the flow control, right? And you will convey the minimum value of the two. So you honor both flow control and the congestion control on the receiver. The idea here is that usually the flows are not limited by the flow control in general. So the limiting factor should be the congestion controller running on the receiver. So essentially, the receive window will in generally express the congestion control window, right? The interaction with the sender's congestion control, again, because the window actually used by the sender is the minimum of the congestion window and the receive window, because the receive window is carrying the LEDBAT calculated window, and LEDBAT will be more aggressive in reducing, so it's likely to have a smaller window than normal congestion control. What usually will happen is that the LEDBAT congestion control will take over and will be the one prevailing because it will be the one expressing a smaller window. So the other thing that we need to take care if we try to do this is we should avoid shrinking the window, right? Because we have this multiplicative decrease, what may happen is that at some point we need to express a window that is half its previous value, right? This is likely to be in most cases more than the number of bytes. The amount that you need to receive to reduce the window is likely to be more than the amount of bytes that you have received in the packet that you will send the ACK for. So if you actually reduce the window in half right away, you will end up shrinking the window, which is not recommended. So essentially what we're going to do is we're going to drain enough packets from the in-flight in order to accumulate enough space in order to be able to reduce the window without shrinking, right? This can be done because you don't do a multiplicative decrease more than once per round trip time, right? So essentially, because you only reduce it once, at most once per round trip time, you have enough packets to drain in order to then be able to express whatever window you want, smaller than it is. So that should be feasible. And then the other problem that actually media suggested when I was talking to her about this a while ago is regarding window scale options, right? Window scale is, as you probably are aware of, a change of the units on that you express the receive window, right? So actually, window scale values between 0 and 1 result in units that are less than the usual maximum segment size, right? So usually that's not a big problem because usually you want to decrease your window size or increase your window size in 1 MSS, or more or less, right? If you have values that are larger than 12, which basically will be 12, 13, and 14, that basically implies that one change in 1 unit in the receive window will be more than 1 MSS, right? And that may generate problems in the sense that your congestion control now is much more coarse because the units it can express itself are much larger than 1 MSS, right? So we have make a set of measurements. We have observed that values between 12 and 14 are very, very rarely used today, right? They exhibit a bunch of other problems regarding window shrinking and other things. So I guess that's the reason why they are not very used today. We would, if we want to go down this path, we will need to probably do a bit more experiments regarding the stability and how expressive the congestion control will be if you use these larger values. In any case, the value of the window scale is set by the client. So the client could actually set whatever, I mean, values between up to 11, right? If he's trying to use LEDPAT or LEDPAT, and that doesn't impose any conditions on the traffic in the other direction. So that can be another way of working around this. So as I said, we're using the RTT instead of the one-way delay. Doing this has a fundamental problem. That is, you include the queuing delay on the reverse path. There's nothing, I mean, I don't think there's much we can do about this. I haven't come up with anything we can do about this. This basically means that you will be overly conservative, that you will react also to congestion in the reverse path. That's it. Right? And we need to deal with a few other issues in order to make this work. In particular, a fairly common case, I guess, it will be pure receivers, in the sense that you're only receiving packets and you're not. So if you're only receiving packets, if you want to measure the round trip time, you cannot send data and match it with the ACK. You will, because you're only receiving packets and sending ACKs. In order to do that, we will use the timestamp options to match ACKs that we have sent and packets that are coming back, data packets that are coming back. So that should work. The other situation that we may have, because we are handling pure receivers, is that because we're going to match an ACK with a packet, we may have an artificial increase RTT because the source is not sending packets, right? So we have identified two reasons why the source is not sending packet. One is because it has no data to send. Well, in this case, either you don't care because you're not managing anything because there is no traffic, or either this happened once in a while. For instance, you have blocks of data that you're sending, right? Every time the block ends, you have some times of period without data. The way we deal with this is essentially we filter. So instead of for measuring the current round trip time, you do a filter of the last n packets. So probably you get rid of that sample that it's outside, that has this artificially increased RTT, right? So probably that should work. And the other case where the sender may not be able to receive data is because you are clamping down the receive window. So if you are artificially telling him that he cannot send because you're reducing the receive window, he won't be able to send. And at that point, the RTT will be increased because you're not allowing him to send data. But that's fine because you actually know when you're doing that. So you can simply avoid measuring while you're reducing the receive window, right? So you can accommodate for this. And the other problem that we have encountered while doing this is regarding the granularity of the timestamp values, right? The timestamp values have, depending on the clock that you use for that, has a given granularity. You may end up with multiple packets going with the same timestamp value, right? So that makes harder to match because you don't know which one matches with which one. Because we don't really need to measure all the packets, just what we simply do is we measure the first one, right? The first timestamp that we send with a given value and the first one that we receive with the same value, and we drop all the other samples that we have, right? And that gives us a proper original measurement of the RTT. Some other design choices. Inter-LEDPAT fairness has been addressed using additive increase, multiplicative decrease. That has been, I mean, there is a paper that explains why this is the case. I mean, I guess this is fairly well understood. Reacting to packet lost, what we do is similar as LEDPAT, we do a multiplicative decrease. The coefficients for multiplicative decrease regarding time and regarding loss do not have to be the same. I mean, we actually play with different values, right? So you have a multiplicative decrease parameter for loss and for time, right? Regarding bootstrapping, what we do is, instead of starting, the problem here is how do you manage to ramp up, right? What we do here, essentially, we start with whatever flow control, whatever window the flow control gives, that is usually a large window, right? And that basically gives enough room for the sender to ramp up, and then we take it from there. And regarding path changes, what we do is the same thing that LEDPAT does, that is we keep a history of the last, 10 minutes, and in order to forget, I mean, we only keep the history for 10 minutes, so we forget measured values that are older than that. So if we change path, we only keep the old path for 10 minutes. So we have implemented this. We have run a bunch of experiments. The experimental setup is very simple. As you can see, we have 2 clients, we have 2 servers. The clients are running Leadbat or else. This is a few results that we have. So for instance, in this case, what we have is a voice call that is using, you have a base delay of 50 milliseconds. You observe here at the beginning that the voice is experience the 50 milliseconds plus a bit of delay. In this case, you see our Leadbat kicking in. We have a target of about 100 milliseconds. We're almost there most of the time, right? And essentially, we show that it keeps the delay bounded when our Leadbat kicks in. Regarding inter-Leadbat fairness, what we have here are 2 our Leadbat flows. We have one that is using most of the capacity when it's alone, right? The second one kicks in. They somehow manage to agree in a reasonable equal split between them. Regarding solo performance, when our Leadbat is alone, the capacity of actually using the whole capacity of the channel depends on the different set of parameters that you choose. I mean, all these experiments have been done with a given set of parameters that we somehow analytically obtain. And what we observe is that roughly, if the round trip time is not very high, you manage to be somehow near full utilization of the link. As the round trip time increases, it has harder time reaching to the full utilization. Again, this is depending on the relationship between the multiplicative decrease parameters, and has a relationship with the fairness issue, right? Interference with TCP. So there are 2 modes of interference with TCP. Either you're reacting to losses, or you're reacting to delay. That really depends on the size of the buffer of the bottleneck, right? If you're reacting to delay, right, if there is enough buffer in the bottlenecks so that you measure the target T, you observe here that essentially you have our Leadbat, then TCP kicks in, our Leadbat goes way down. It just basically stays with a congestion window of 1, gives all the rest to TCP, and then when TCP disappears, our Leadbat kicks in again. And if there is not enough buffer in the bottleneck in order to observe the target delay, then both of them will react to losses. But because of the parameters that our Leadbat is using are much more aggressive than the ones that TCP is using, what we observe is that our Leadbat uses more than what it used when it has the delay base, but overall, it leaves most of the capacity to TCP. So, okay. So the other thing that we have done is we have played with Leadbat++, stuff that Praveen will present. And essentially when they are both competing, they play nicely with each other, more or less, right? When TCP enters, both of them disappear most. And then when TCP goes away, they share again the capacity equally between them. Okay, and then in order to wrap up, I mean, I was wondering if this is the type of stuff that ICCRG would be potentially interesting working on.
Thank you, Marcelo. I just changed the question a little bit and see other people here who would like to who would be interested in working with Marcelo, or even importantly, at least in my mind, people would be interested in seeing something like this deployed. But yes, questions? We have just a few minutes.
Jake Holland, this is very cool work. Thank you. I might be, I'm not sure I have time, but I might be interested in looking at this. I guess that's all I want to say for now. Thank you.
Thank you.
Neil Cardwell, I think this seems like very interesting and generally useful work. Is this? I had a couple of questions. Is this work so far in a simulator or with?
No. This has been done in an. I mean, we have a Linux implementation on this, and we have a bunch of virtual machines and I mean a virtualized environment.
Okay. Excellent. And then maybe you mentioned this, but I missed it. How do you imagine picking the delay target or delay budget?
Sorry, once again.
What's the plan for picking the delay budget? Or
What we have done is as lame as using the LEDBAT one. Okay, that is 100 milliseconds.
Okay.
Praveen has been using 60 milliseconds in LEDBAT++. So, I mean.
Okay, thank you.
I mean, there is some rationale in the RFC on why 100 millisecond makes sense, and there is some rationale why I'm just leveraging on them to do. Yes.
Mr. Huang, actually, I also like this work because we have similar thoughts, but quite differently. My questions are: is there any plans like can work for ECN signals or something?
Sorry, I cannot hear you.
Okay. My question is, and Rachel Huang, is there any thoughts in the future that could also works together with ECN signals?
With ECN signals.
Yeah.
So with ECN is, as if I understand it correctly, it will essentially be the same as loss. So the response to this will be the same as loss, right?
Okay.
So I mean, I understand that's what LEDBAT does. Media?
Sorry?
No, I'm asking media. LEDBAT reacts to ECN marks as the same as losses.
Okay. Yeah.
Correct?
The whole point about LEDBAT is that you usually try to avoid losses and also try to avoid the situation where you get ECN signals. But if you get ECN signals, it's the same reaction, and it's the same reaction as Reno.
Right.
Okay. Also answer the other question about the delay target. This whole thing was proposed by BitTorrent at some point, and they also had a lower delay target at the very beginning. And then they increased it to 100 milliseconds at some point because their scenario was mainly to avoid congestion basically in the home router where the buffers are usually very big, while still having a Reno-like behavior in the core network where buffers are smaller and you can compete like equally. And the rationale which is in the draft is that you want to stay below 150 milliseconds because that's the maximum you can cope with for like any kind of interactions between humans.
Right. Thanks.
Thank you so much, Marcelo. Please find him and talk to him if you're interested in more work. And I'm hoping that this actually gathers some steam because I think this is a very different type of work in that it's receiver side. And I do think that there's a lot of value in this, and the motivations that Marcelo mentioned are very important. So thank you again for the work and for presenting it. We're going to move on to the last presentation, which is Praveen. Praveen, can you come up? And hopefully we can do this. You're on, Praveen.
Okay, I'm going to try without the camera. If you can hear me, please say yes.
We'll just give it a moment. Can you try again, Praveen?
Yeah, can you hear me?
Yes, finally.
Yay. Sorry for the mishap there with the headset. So I'm going to go do this without video to make it easier. So this is LEDBAT++ congestion control for background traffic. This was originally presented in IETF 100. That presentation included some test results and graphs. Today I'm going to skip over them because of lack of time. But this is going to recap the algorithm, and then I'm going to talk about next steps. So let's go to the next slide. So this is a quick recap of what LEDBAT RFC 6817 said. It's a less than best effort congestion control algorithm applied on the sender as opposed to the receive side presentation that Marcelo just did. The goal is to compare, it's a delay-based congestion control algorithm. So you measure the minimum observed delay over an observation window. If the currently observed delay is less than your target, then you increase the congestion window. If the delay is higher than target, then you decrease the congestion window. The original RC did not have any strict requirements on slow start. There was a suggestion to avoid it. And it also reacts to packet loss because the goal here is less than best effort. So it reacts to packet loss and other congestion signals, just like standard TCP. Next slide, please. So we found a bunch of problems with LEDBAT, both documented in existing research as well as found through our own experimentation. So some of the problems, so with TCP, one of the problems is one-way delay measurements. There's no standard clock frequency, and there's also like a clock skew problem. So we could come up with like custom schemes to solve this, but those are very difficult to get right in practice. The other problem that LEDBAT has is a latecomer advantage. So if one flow starts early and then LEDBAT enters the network later, then it measures a higher base delay and it will inject more delay into the network. It will not be able to detect that there's other traffic and back off. There's also a well-known inter-LEDBAT fairness problem. There's a paper there that you can refer to. So if you have multiple LEDBAT flows, it results in a stable queue, but there's no fair sharing. Of course, the problem with slow start, what should be done for like background connections. There's also a latency drift problem, which is very interesting. If you have a very long-running LEDBAT connection, which is possible with like large background transfers, file uploads, photo uploads, and such, the connection keeps measuring a higher base delay over a longer period of time. This ratcheting effect is very easily reproducible in even in lab measurements. And then there's the low latency competition problem. So if the link is actually very good and the latency is very low, then the target delay is never reached. So LEDBAT competes very aggressively with standard TCP. So our goal with LEDBAT++ was to solve all of these problems. Next slide, please. So this is implemented currently as a congestion control algorithm for TCP in the Windows operating system. The enhancements over LEDBAT are the following. So instead of using one-way delay measurements, we use round-trip time measurements. We do slower than Reno congestion window increase. So there is an adaptive factor that we introduced for ramping up much slower than standard TCP. Similarly, when we react to loss, the decrease is multiplicative, but the reduction factor is again adaptive. And then the slow start is modified in several ways to be slower than Reno, as well as to incorporate mechanism that is very similar to high start. We use delay as a signal to exit slow start. And the most interesting one is the initial and periodic slowdown, because some of the problems mentioned require measuring a very accurate base delay. For that, you need to yield traffic so that you're able to measure the accurate base delay. This has been shipping as part of Windows for a while. It's currently in use by several scenarios and pretty broadly deployed at this point. Next slide, please. So why round-trip time latency? It's pretty easily available. It's already implemented in TCP. Of course, the disadvantage is that we will measure delay in both directions. So because this is a less than best effort algorithm, it's okay to be more conservative than what you ideally like. There's of course the other problem of receiver delays and delayed access in TCP, which need to be accounted for if you're measuring round-trip time. So some of the mitigations for these problems are to enable the TCP timestamp option by default and to filter the RTT samples. This is actually a suggestion from the original LEDBAT RFC. So pick the minimum of the most recent 4 RTT samples. And we use a target delay of 60 milliseconds. This value is very deliberate. I noticed there was a discussion about this in the RLEDBAT presentation, but this value is very deliberate. So because of VoIP, the acceptable delay is 150, and if your target delay is 100 milliseconds, it leaves very little room for all the other delays, like propagation delay and receiver delay. So that's why we picked the value of 60 milliseconds, and it's also larger than the typical TCP delayed ACK timeout on both Linux and Windows now. There are of course like legacy systems which use higher values, but in practice this works out very well. Next slide, please. So what is slower than Reno? This is basically introducing that reduction factor F. And that factor is not a constant. It's a dynamic value based on the ratio of the target delay and the measured base delay. And we pick a maximum of 16 because it gives us a trade-off between responsiveness and performance. Of course, implementations are free to experiment with that value, but we find 16 to be a really sweet spot. This solves basically the low latency competition problem. So if you deploy LEDBAT on a low latency link, it will still be less than best effort. It will not interfere with foreground flows. The next slide, please. So this is to multiplicative decreases to solve the inter-LEDBAT fairness problem. This was actually suggested in the paper that was referred to earlier. Again, this introduces a reduction factor here. And we also specify the values that we experimentally arrive at. So using the constant value of 1 and the decrease coefficient to be 0.5. The other thing that needs to be ensured is that the condition window never drops below 2 packets. So this is required so that middle boxes don't time the flow out. So you don't want long periods of silence. So you maintain at least a minimum rate through the network. Next slide, please. Original slow start is exponential, and that can cause like massive loss, and it also cause other flows to back off. So what we do here is 3 things. First, we apply the reduction factor F to the condition window increase during slow start. That makes it slower than Reno. We also limit the initial condition window to 2 packets versus the de facto standard of 10 packets now. And there is a high start like mechanism. It's not exactly high start, but very similar. If the queuing delay is measured to be at least 3/4 of the target, then we exit slow start immediately and move into condition avoidance. But this high start like algorithm is only applied during the initial slow start. Subsequent slow starts usually recorded as its threshold. Next slide, please. Initial periodic slowdown. So periodically, LEDBAT++ will enter the slowdown phase where the condition window is again frozen at 2 packets for at least 2 round trip times, and then it will do slow start again back to its original SS thresh value. And the goal here is to not have more than 10% drop in throughput because we are probing for RTT. So the way we calculate that is from the entry of the slowdown and the time taken to reach up to SS thresh, we multiply that value by 9. So it's effectively it's basically a round of like 10. This solves the latency drift problem. It also helps with solving the latecomer problem. Next slide, please. So the draft was submitted just yesterday. I don't know if people have gotten a chance to read it, but please do read it and give us feedback. There is a RANSI IPR disclosure that we just posted. I think the number is 3651. I couldn't get it in time for this presentation, but I'll make sure the slides are updated later. And the next step would be, should this document be adopted in ICCRG or some other working group? From our point of view, this is widely deployed at this point. There are a few research areas for future, but this is production ready. Questions?
I don't know if you have any time for questions, but if anybody has a burning question, come up to the mic like right now. Are you going up, Neil?
I was just a little curious about the 60 millisecond threshold. Were there experiments with lower values? It would be great if a lower value might work.
The main concern is the delayed ACK timeout used by the server. So even though we filter RTT samples, it's still possible that there would be problems if we used a lower value. I think Linux delayed ACK timeout is like 40 milliseconds, so that's the reason we picked a value higher than that. But again, this value is certainly subject to more experiments.
Jay Collin, also on the choice of the target delay, is there some reason not to use a dynamic value to discover it? and try to like adjust to a difference?
It's certainly possible. Again, like yeah, I think the value is certainly open to more experimentation, but in practice, this value really works well on a variety of networks.
Thank you.
Ian Sweat, Google. I have a specific request, which is it possible that you can make the value configurable based on the max stack delay? Because in new transports like Quick, we now explicitly communicate that value. And that would make it more useful in things like Quick.
That's a great suggestion. Yeah, for Quick, we can certainly do that.
Nicolas Kuhn from CNES. I have 2 points to make. First, CDG is in the Linux kernel and has a lower than best effort mode. It might be worth considering in the evaluations. And also, AQMs has shown to be a big problem for let back proposals in the past. So basically, you're not lower than best effort anymore. Maybe you should have AQM tracing. So the previous presentation and this one, it's worth evaluating all these works when you have an AQM on the path.
That's good feedback. Thank you, Praveen. I hope that the feedback was useful about the question of adopting. Let's take that to the list. We still need to figure out what that really means. But I think that will resolve this along with the other question of how we are going to adopt documents. But thank you for the presentation, and thank you, everybody. See you all in Singapore on the list before that.
I would like to ask a quick question of the room. How many people think that 3168 is a barrier to progress?
Find Matt in the corridor and tell him. Bombshell at the end.